denotes a normal vector, actually, a vector that is perpendicular to both. Okay, and then we can also interpret PU cross PV as the area of this small chunk of rectangle on to this area actually. Okay. Anyway, so we interpreted these PU cross PV as the tangent vector in the principal directions, okay, along U and along V actually. Okay. The coordinate lines, we call them coordinate lines last time. So we define the surface now. Roughly. We know what the surface, what we mean by an oriented surface. So the next thing that we would like to do is to define, and so what we did, for example, analogously on curve. So we defined, for example, curve, and then we concatenated them. We can do something similar here, but let's not get into the concatenation. So the next thing that we did in our curve theory was that if you have a curve parameterized by a regular path, then how to compute the length of it actually. So you can ask an analog question actually that, okay, if I have a parameterization and that parameterization is defining a surface, the question is, what should be the surface area of it? Okay? So what should be the surface area of it? Alright. But let me start by defining a normal to a surface actually. So here's a definition of a normal vector to a surface. So let S is a subset in R3. Okay, it's an image of set in the R2. Okay, under P actually. Okay, so let S be a surface in R3, and imagine it's an oriented parametric surface actually. Okay. I'll talk a bit about the orientation as well. Okay. Then, so I have a surface, and I'm taking a point, for example, on it. Okay. And maybe these are two coordinate lines that pass through this point, and I know that I can draw a tangent vector that is going to be PU along this vector and PV. Okay, and then I would like to draw an outward normal vector to the surface actually. So what would be this outward normal vector?
So cross product.
Then I can say, so let me define the normal vector to the surface. Okay. As so it's going to be a function of v of uv, or maybe a function of u comma v. Okay, but how are you going to define it? You're going to say that, okay, let's take this pu cross pv vector. Okay, so this pu cross pv vector is actually normal. Okay, and then divided by magnitude of it so that it becomes a unit normal vector. Okay. So you want to find a normal on a surface, then you're going to say, then just take the cross product of these two, tangent vectors, and that's going to give you the normal vector. Okay. But now, by definition, think about it. By definition, S is a surface. S is a kind of a object. For which PU cross PV is never zero. Okay, at all points UV. This means that normal would always exist. This would always exist on the surface. So no matter what point you take onto the surface, you can always draw a normal vector actually. Because this is never zero. So the situation is going to be tricky when this can be zero, but we are excluding all those points, UVs, for which the PU cross PV is zero. We are not interested in those points actually. Okay? So by definition, you can always draw a normal vector onto a surface actually. And if you have a kind of a surface on which you take any point and draw a normal vector, you call such kind of surfaces as the oriented curves, oriented surface actually. Okay, oriented surface. Because these are the kind of the surface for which you can say that okay, this is inside and outside actually. Okay, so it makes sense to have inside and outside, or you can have up and down actually. Okay, so for example, Mobius strip is not oriented because there is no inside and outside in that case. So whatever is inside, if you move along the Mobius strip, it becomes outside actually. Okay, so we are only interested in those kind of surfaces for now, parametric surfaces, on which you can always draw a normal vector. So you can always say, okay, it's above, what do you call the surface, or below the surface, or inside the surface, or outside the surface, okay? And you call such kind of surfaces as the oriented surface. Okay? They have a certain kind of orientation.
इसको थोड़ा repeat करना inside outside concept.
And think about it. So if I have a surface, okay, so I can say it's kind of a good surface in the sense that you take a point and draw a normal vector actually. Okay, so I'm going to say that yes, the entire surface is below this normal vector roughly. Or I mean, if you want an inward normal, okay, you want that something is flowing inside, the surface, then you can say that okay, the entire surface is, above the surface actually. Or the normal is pointing inside the surface or outside the surface actually. Okay, so you're going to call such surfaces an oriented surface actually. And so usually we deal with the oriented kind of surface. For example, if you treat this room, then these walls are creating a surface, but it's an oriented one because there is a notion of inside and outside to it. Okay, and you will always have an inside and outside. Okay, for a surface if this guy exists everywhere. Okay, so that's a guarantee, that's a kind of a sufficient condition that if this guy, the normal vector, exists at all points on a surface, so it's a sign that that surface must be an oriented surface. Okay? समझ आ रही है?
Yes.
Good. So now the next thing I would like to have.
इसको यूनिट नॉर्मल क्यों कर रहे हैं?
क्या मतलब?
तो नॉर्मलाइज करते
I mean,
हैं.
you can keep this vector as it is, but if you divide it by the magnitude of it, in many cases your calculations becomes easier to do actually. Because I mean, if you have to do the magnitude, it's 1. Okay, so normalizing a vector is out of its convenience. Okay, so you can take it. Don't want to normalize it, it's fine. But normalizing is just because of its convenience actually. Take it. I must say that this must be true for all u and v in the domain, whatever the domain of the function is. Okay. Okay. So can you find the so imagine you have this long patch. Okay, imagine this f is f from u to r is a smooth map. Okay, and u is a subset of R2. Okay, so it's some open subset in R2. Okay, then we talked last time about it that this, but P of uv equal to this is a Mount patch. It's a graph surface actually. We call it a graph surface. So this is just a fictitious picture of a graph surface. Okay, it's a graph of a map F. Okay. Now, what will be the normal over it? So what are you going to do? So we can compute it. So I can compute PU is going to be 1, 0, and FU and PV is going to be 0, 1, and FV, and the PU cross PV can also be calculated. Okay, it turns out that it is going to be minus FU minus FV and 1. Okay, so the normal vector okay, at an arbitrary point of a graph surface is going to be, this f minus fu minus fv, negative f1u, negative fv1, and everything divided by the magnitude of fu square plus fv square plus 1. So this is going to be the, so you know how to do the calculation, it's not a big deal. Okay? It would be an interesting question to ask that I know that this normal is depending on this parameterization. Okay, so I have a surface defined through a parameterization. But what if I change the parameterization? Would my normal vector would also change actually? Or what changes would take place in the normal vector when I compute a normal vector through one parameterization? Okay, so we can prove that the normal vector at any point onto the surface is independent of choice of the parameterization. No matter what parameterization you choose, it would always be roughly the same actually. Okay, so it's a well-defined, kind of a map. Okay. So maybe this would be a good exercise to show that, prove that n is well-defined, normal is well-defined. And by well-defined, I mean, if you reparameterize it, the formula for computing normal vector would be the same. Okay, so it's not going to change. So you can use another Q that is really the P composition phi and compute the normal vector for P, and you will see that it should be the same. And obviously the phi is diffeomorphism, so we discussed it in last class. Alright, normal vector. The next thing is how to compute the surface area. So what do you think, what should be the intuitive way to really compute the surface area?
So हम उधर कह रहे थे कि पार्शियल u पार्शियल v p का जो था उसकी अगर क्रॉस प्रोडक्ट ले रहे थे तो एक छोटे से चंक.
It's very intuitive. So in other words, you take this domain, and I know that it can be matched. I know that through P I can map it, say for example, onto the surface, okay, and I can take a point, for example, okay, and draw these two tangent vectors, and let's assume that these rectangles are pretty small, they are not bigger in the quantity. Okay, so pu cross pv, okay, so pu cross pv, and then this area is going to be really the magnitude of the pu cross PV. So the magnitude of PU cross PV is giving you the area of this small chunk. So what would be the next thing that you should do?
Integrate.
Add them all. So do the double integral. Okay, with respect to
u and
du dv. So what is du dv and what is this relationship with pu cross pv? So du dv is really this small rectangle, and under P it's mapped onto this rectangle actually. Okay. Okay. So what you are saying is that you sum up all the areas of such rectangles. Okay, du dv, and what would be the limits on the du dv? So it depends on the domain. So if this domain is the u, so you need to integrate this over the u actually. Okay. You have to integrate this over the u. So that would be the surface area, the area of the surfaces. Okay. The area of the surfaces.
Single integral sum क्यों नहीं कर सकते सर?
Thank you. Think about it. So here you are in two dimension actually. It's not going to be a single integral. Okay, so that's a this number is coming out of a two dimension. So, okay, so you are splitting all these, okay, into such small rectangles. Basically what you are doing is that you are splitting the domain into such small rectangles and then mapping them onto the surface, and then on each, you are trying to find the area of each rectangle, okay, by drawing these two tangent vectors and calculating their cross product so that their magnitude will give this area, and then you want to sum them all up actually. Okay? Because each of these small tiny rectangle is a consequence of a small tiny rectangle here actually. And then you sum up all those areas, is going to give you the area. Okay? So what would be the surface area of a graph surface? Any? What would be the surface area of a graph surface? You're going to say it's for the graph surface I know that Q cross PV is this. Okay? And so this is going to be the square root of f square plus fv square plus 1 and du dv and over u actually. So that's really the surface area of a graph surface. Okay.
Sir.
So if I have a graph surface, the surface area would look like this. Now that's a beautiful simple formula. Think about it. Why this guy is a beautiful simple formula? Okay. Because this simply asks that give me just f. Okay, so give me f. Okay. So any, what do you call it, scalar field, not a scalar field, but guess a scalar field, okay, that takes input from R2 and throws them in R, okay. So give me any f and I can find the surface area of its graph actually, okay. By doing what? By substituting, say for example, fu and fv here and solving the integral, you're going to get the surface area of the surface. Take for example, if I say that okay, I have this function f of u equal to u square plus v square, okay, and where the u and v are, for example, chosen from this rectangle 0 to 1 and 0 to 1, something like that. This is square. Okay, and then I'm asking that okay, what would be the surface area, of the graph of this f? So what I need to do, just take this, substitute it here and solve your integral. Take a simple double integral and you can get the surface area. Just very much nice. It's really analog to the length. So you have the previously curve, you chopped off the curve into the small straight lines, and then you sum up the straight lines and that give you the, what do you call, the length of the curve actually, and you are precisely doing the same actually. So you're saying that okay, you want to find the surface area of a surface, you chop off your surface into the small rectangles, and the way to chop off your what do you call surface into the small rectangles is this pu cross pv that can give you the area of each small chopped part, and then integrate them all, and that's going to give you the surface area. So it's very much natural. Okay. So what should be the next thing? So all this description is here. Second thing, okay, let me show one of the things. This surface area that I have defined in this manner is well defined. In other words, it's independent of choice of the parameterization. No matter what parameterization you choose, the surface area would not change actually. Okay? No matter what parameterization you choose, the surface area would not change. Okay? So A of S is well defined. Surface area of S is well defined. So what you need to do? So let's take another reparametrization of the parametrization P, and let's take this parametrization and compose with the diffeomorphism actually. Okay, so the compose with the diffeomorphism. Then how this QU cross QV and PU cross PV are related? Remember the area of such rectangles. Yes, so PU cross PV and Q cross PV and QU are related by multiplying the determinant of the Jacobian of the diffeomorphism. So it really gives you an equality, a relationship between both. Okay. So we're going to do. We're going to do this. So here's the thing. So I have an integral, this PU cross PV, PU PV, okay? And I would like to change it in the terms of, you know, I'm composing my parameterization for some phi and changing it to the Q actually. So how this integral should be related with, for example, you know, we कह सकते हैं du dv होगा, or maybe you call it du prime and dv prime, it doesn't matter. But how the du and du prime and dv prime should be related with each other. So you just need to multiply determinant of the Jacobian actually, determinant of the Jacobian. Okay? Okay? And the magnitude of du cross. As in, so that's how they are related. And now this Jacobian is a number, so I can insert it inside and I can use this fact and I can say that, okay, so here you are integrating over u, but this would be integrating over v, and you remember that phi is a map from u to v, where v and u both are the subset of R2, okay? So you have to keep the notation in head all the time. Okay, so I'm going to assume that you remember your previous notation. Okay, so I'm not going to get into the tiny details of the notation. So now you have this integral over v. Okay, you have this integral over v, and this will turn out to be pu cross qu cross qv prime and dv prime over v. Okay. And this u prime and v prime are just dummy variable. I mean, if you wish, you can just you can just change everything u prime v prime to uv, and it's not going to change anything. As so I have this x square dx from a to b and z square dz from a to b. So does it going to change anything? It's not going to change anything.
So लेकिन du dv एक rectangle को show कर रहा है.
I'm just indicatively using du dv. So if you wish, you can still keep du dv, but this du dv, you know, I'm just denoting it by same du dv so that I don't need this multiple notations actually. So it's just making it. And what does this show? Both parameterizations are given to the same surface.
du prime और dv prime दे रहे हैं.
Actually, but
Jacobian की वजह से आ रहा है.
but so what you are doing is that you are transforming the entire surface into it. So I have this surface on which I have these rectangles, and then I'm taking this surface and I'm applying the q over it. So I'm applying phi over it. Okay, maybe. So the q is taking me from this. Okay. So I have this surface. No. So the better way to say this. The better way to say, I know that I have a domain. Okay, that is U. Okay, and I have said that I have a phi. Okay, and this is V. So phi is taking me from here to here. Okay, so phi is taking me from phi to P, and P is taking me to the surface actually. Okay, so P is a direct map from, for example, U to the surface. But I can reach through another way to the same as well actually. Okay, so it's going to be, through this Q. Are you getting the point? So you take this Q and you reach from, what do you call, P to the same surface V. So du dv prime, and relationship between du dv prime is this actually. So this is a rectangle, say du dv, and here this is your du prime and dv prime actually. And phi is the changing, transforming the one kind of rectangles into the other kind of rectangles actually. So if phi is a diffeomorphism, through Jacobian, I can have an equality between these two areas actually. पहले भी पढ़ के हैं change of variable formula. So what was change of variable formula? That you have two-dimensional domain, ठीक है? You want to apply some diffeomorphism and turn it to another domain and integrate over it actually. ठीक है? Then you need to involve Jacobian in between into your integral, that change of variable formula. And that Jacobian is going to basically provide you kind of equality between areas of rectangle. ठीक है? बता दिया बात. समझ आ रही है बात? Okay. So it's a well-defined map. It depends on really. So surface area is well-defined. So I just showed one, and rest of the things I'm going to say that true for yourself. That if I'm defining something, okay, using parametrization, that definition is independent of choice of the parametrization for the surface. ठीक है जी? Okay. All right.